Hello, everyone. So, for this playlist, I've thought of covering some important concept related to maths, which are actually very important when the question is related to some coding round, especially. In the coding round, the questions are sometimes related to modulo inverse, modulo arithmetics, uh, using the sieve algorithm basically for finding prime numbers, uh, SPF's finding, I mean smallest prime factorization. So not the exact codes for that, but there are some questions where you will need the concepts of this programming algorithms so that you can proceed it in an optimized manner. Okay, so there are basically three main topics which I wanted to cover under maths, and there are some questions related to all those topics. Uh, Wherein the first is modulo arithmetic, then sieve, and then SPF, smallest prime factorization. Sieve and SPF is somewhat related to each other, and modulo inverse is modulo arithmetic is a different topic from both of this. Okay, so now what do I mean by modulo arithmetic? Modulo, you might be simply knowing that, let's say, modulo is nothing but remainder. Okay, remainder when you divide a number by, let's say, a modulo b means remainder. Remainder when I divide a by b is what my modulo actually means. That when I divide a by b, whatever remainder I get is the a modulo b. Okay. Okay. So for two numbers, uh, x and y, and I'm considering modulo as m over here, capital M, and for modulo m, this x plus y whole modulo m is nothing but, you can give this modulo separately to x modulo m plus y modulo m whole modulo m. Okay. For subtraction also, you can give it separately. X minus y modulo m is nothing but x modulo m minus y modulo m whole modulo m. And for same case for the multiplication, x multiply by y modulo m is nothing but x modulo m multiply by y modulo m whole modulo m. But this couldn't be the case for division. Okay, this couldn't be the case for division. Okay, this shouldn't be the case for the division, because for division, what you have to do is, if it's x divided by y modulo m, then it should be x modulo m multiply by y inverse, or I should write it with the pen, then okay, this is nothing but x modulo m multiply by y inverse modulo m whole modulo m. So this, the main logic for doing this is finding modulo inverse. So our main concept of today's topic is to find modulo inverse. Now, how we will find this modulo inverse? Okay, so there are basically two different techniques to find the modulo inverse. Our first technique of finding the modulo inverse is extended Euclidean algorithm, and this is generalized algorithm applicable to every m, applicable to every m. I mean, whichever modulo m was given in the question, this should be applicable to every m. Now, what is this extended Euclidean approaches? The extended Euclidean approach says that you can do this when m and x are coprime. What does this mean? When m and x are coprime is GCD of m comma x is 1. So no, this is not applicable to every m. This is applicable when this m and x are coprime. That means if I have to find x modulo m, sorry, if I have to find the x inverse modulo m, then I can apply this method only if GCD of m and x is 1. So they are coprime. So let's say GCD of 2 and 15 is 1. Okay, GCD of 2 and 15 is 1. So if I wanted to find uh, 15 inverse modulo 2, I can do it. I can do it. Okay. Now consider two integers. Consider two integers a and b, and then find their GCD also. Find their GCD and also take two more variables x and y, such that a little bit of maths, a little bit of proof, so that you didn't have to remember everything. This Euclidean algorithm, we're not going to use it much. We're going to use second approach, which I'm going to tell you. Okay, but still, it could be useful for some of the cases where second approach will not be applicable. Okay, such that ax plus by is equal to GCD of a comma b. So I should get some x and y such that if I multiply x with a and y with b, I'll get the GCD of a comma b. Okay, now to find the multiplicative inverse of a, to find, I'll write this mi, this is multiplicative inverse of capital A under modulo m, under modulo m. Then I need to replace this a, the small a, so replace small a with capital A, because that's what I have to find the multiplicative inverse of a, under which modulo, and small b with capital M. Okay, so my equation is capital Ax plus my is equal to 1, and we have already told that this should be possible when this whoever's multiplicative inverse we have to find and that particular modulo, if they are co-prime, then only it's possible. So this is possible only when ax plus my is equal to 1. Okay, now if we take the modulo m on both the sides, okay, so I'm taking ax plus my whole modulo m is equal to 1 modulo m. Okay, mod m or modulo m, whatever if you want you can write. So now then this ax modulo m plus my modulo m, now my modulo m will always be 0, because something is the factor of m. If I'm doing the modulo with the m, it will always be 0. So this will contribute to 0. Okay, so I'm left with ax is equal to 1 modulo m. So what does this simply means? That x is modulo inverse of a. Multiplicative modulo inverse. This should be multiplicative modulo inverse of a. So x is my multiplicative modulo inverse of a. Okay. Now we have the code for this also. What does this code say is let's say you have to find the modulo inverse. So we'll have one function saying mod inverse, and you have to find the modulo of a under m. So we have these two variables. Okay, I'll take two another variables x and y, and I'll find the GCD extended for this. Okay, so the GCD of I'll find the GCD extended for this, which will give me the value of this. Actually, it will give me the GCD only, but it will place this. It will place this values of x and y also. Basically, your answer is x, so you'll get that. So GCD extended, I will find for a, m, x, and y. Why am I passing with m%? Because I wanted to set this values when I'll run this function of GCD extended. Okay. So if G is nothing but it's GCD only of A and B. Okay, of A and M. It's the GCD only of A and M. But while finding GCD, we have to set these values x and y. So we cannot directly apply that underscore underscore GCD STL function. That we cannot apply, because we have to find GCD, and alongside finding GCD, we have to set these values x and y. Okay, so if this GCD is not equal to 1, that means these are not co-prime. So then this inverse does not exist. Okay, this inverse will exist only if the values are co-prime. Otherwise, your result will be what? X. So it's x modulo m plus m modulo m. Now this is another concept which I wanted to explain in a different color. Let me write this. So what I'm doing, okay, I got the answer as x. I modular, I have done modulo with the m, and then I've added m. Why? So let's say you have x as 2 and m as 5. Okay. So then 2 modulo 5 is what? 2. Okay. And let's say you have x as 7. And 7 modulo 5 is what? Again 2. 5 and 5 and 2 will be remainder. So 2. Now what is for x is equal to minus 3? Now you didn't know what could happen for x is equal to minus 3. So minus 3 modulo 5 should give me minus 3. But minus 3 could never be my remainder, right? So what should I have to do? I have to add 5 in that, and then I have to again do modulo 5. So this is 2 modulo 5, this is 2. So minus 3 modulo 5 is nothing but 2. Minus 3 modulo 5 is nothing but 2. So for negative x, for negative x, I have to add m to make it positive after doing modulo with it. So for negative x, what I have to do is x modulo m plus m. This will make the term greater than m at least, and then you have to do modulo m. I hope you are clear why we are doing this point. This we have to do every time we feel like our remainder, our x could be negative, then you have to do this way so that your negative cases will be handled. Okay, fine. This is another box which you can make. Let me shift to our original color. And now we have the function of GCD extended, from wherein we will find the value of x and y. GCD extended. This will take int a, int b, int x we have passed with ampersand, so we'll take it with star over here, and y. Simple code for finding GCD is, if your a is 0, okay, you have your x and y as 0, and your GCD of a and b will be nothing but return b. Otherwise, every time you have to take two variables. Let's say I'm taking x1, y1, and I will find the GCD with this recursive approach, wherein my a will be now b modulo a, this will be a, this will be x1, and this will be y1. Now your x will be y1 minus b by a into x1. This is again a little bit of more proof, but you can remember this simply. And your y1 is again x1, and you will return GCD. If you want, I can put the link of GFG below where you will find the exact proof of all these things. But no need of remembering this, because this approach will use it very, very, very less frequently time. Okay. More often we are using the next approach which I'm going now. So this actually you can ignore. So the second approach says that, let me change it a little bit. So this is for applicable for all m, okay, and you will find the inverse only if GCD of a comma m is 1, then only inverse is possible. Okay, so that is the common thing. But the second condition is when m is prime. Okay, GCD should be 1, but m should be prime. Anyways, if m is prime, GCD of a comma m is 1 only, right? Okay, so when m is prime, we can use a Fermat's little theorem. What does it say? Fermat's little theorem says that when m is prime, a raised to m minus 1 is equal to 1 mod m. That's what Fermat's little theorem says. A raised to m minus 1 is equal to 1 mod m. Okay. Now, I can multiply a raised to m on both the sides. A raised to m minus 2 on both the sides. Okay. So, if I multiply a raised to m minus 2 on both the sides, I'll get a inverse is equal to a raised to m minus 2 mod m. Okay. So, a inverse is what? A inverse is nothing but, if you have to find the inverse of a, I have to do a raised to m minus 2. Power of a, comma m minus 2. And that is my inverse of a. In most of the cases, in most cases, in our questions, m is given as 10 raised to 9, 1e9 plus 7. Okay, which is prime. If you have seen until now, we have find this, uh, we have done the solve the questions wherein m was given as 1e9 plus 7 only. So, but this is prime, and we can use simply the above method itself. Okay. So now our mod inverse is like mod inverse int a int m. Now directly we will do what? GS, not GCD extended we have to do. We can write underscore underscore GCD of a comma m if G is not equal to 1, and that means inverse does not exist. Okay. This is the basic condition. For inverse to be existed, this GCD should be 1 of a m and n, a and m. Otherwise, we will return what? Power of a comma m minus 2 modulo with m. So we'll pass this. Now again you need to observe the power function. How we will write the power function? Okay, there is a STL directly function, STL function called POV, which will calculate the power of a raised to b. Okay, but it internally what it does is it will multiply a b times. So it will run a for loop 0 to b, okay, less than equal to b, I plus plus. It will run one for loop and it will multiply a b times, a into a into a into a into a. How many times? B times it will run. This a into a. Okay, so this could not be possible when b is 10 raised to 9 plus 7. We cannot run a for loop for 10 raised to 9 plus 7 times, right? So we have to find the optimized method. This will take order of b time complexity, which is not feasible in our case when m is 10 raised to 9 plus 7 and we have to find a raised to m minus 2. So again, we need to find some optimized approach for power method. So optimized approach for finding power. Now, let's say you have to find 2 raised to 16. Then what you will do? What you will do? You'll do 2 raised to 8 into 2 raised to 8. This is 2 raised to 16. Again, I'll divide this as 2 raised to 8 is what? 2 raised to 4 into 2 raised to 4. Okay. 2 raised to 4 is what? 2 raised to 2 into 2 raised to 2. So if I divide this power by 2, 16 by 2, I have to do this by 2 by 2 by 2 until how many times? Until I'm getting 2 raised to 0, which is 1. So something power 0 is 1. So let's say if I'm doing x raised to y, okay, I'm considering this y as even. Okay, considering this y is even, then if y is 0, we will return what? 1, because something power 0 is 1. Otherwise, your power function will called by x raised to y by 2 into m modulo m, and you will let's say this is p, and you will return what? P into p. Simply p into p, right? Whole modulo m. This modulo m should never be forgotten. Everywhere it should be written. Okay, I hope you got. But what if y is odd? So let's say in above example, if you have 2 raised to 7, what you will do? In above example, if you have 2 raised to 7, then what you will do? You will do, you will separate out 1, 2, and then you have 2 raised to 6. So this is 2 into 2 raised to 3 into 2 raised to 3. Again, this is odd. So what you will do? You will separate out 1, 2, and this is 2 raised to 2. So if y is odd, I will do the same thing, but p into p multiply by x also. So one time I have to multiply this x. One time I have to multiply this as x raised to y. So this will be done. X raised to y by 2, x raised to y by 2 will be done. But one x is separated, that I have to multiply it separately. So my power function will be like, now you'll be given with x, y, and m. So for finding modulo inverse, this x should be a, this y should be m minus 2, and m should be m only. Okay. If y is 0, this is the base case, you will return 1. So now our power functions optimized time complexity is order of log of b. Okay, because I'm dividing it by 2 by 2 by 2, so I've reduced it order of log b. This 2 raised to 16. I'll not run 16 times. First it is 8, 4, 2, 1. Only 4 times. So it's log of 16 only. I hope you got. Okay, so we have reduced the time complexity, and log of 10 raised to 9 plus 7 is 9 only, right? So that is possible, feasible. If y is 0, we'll return 1. We'll have one p, which is nothing but power of x comma y by 2 into m whole modulo m, and I'll make this p as p into p. Okay, now while returning, what you have to do, if y mod 2 is equal to 0, that means if it is even, I will return p, else I will return p into x modulo m, and this time complexity is order of log m. Okay, so overall time complexity to find modulo inverse is also log m only, because I'm doing nothing, I'm just calling power of a raised to m minus 2. So modulo inverse is also the order of log m. I hope I'm clear. Okay, so we learned two different approaches, Euclidean, extended Euclidean algorithm, which will rarely be used if m is not prime. If your m is not prime, then only you are uh, bound to use that extended Euclidean approach. Otherwise, you can simply use this Fermat's little theorem, wherein A inverse is nothing but power of a raised to m minus 2 whole mod m. And this power method also we have done it in optimized way in log m time complexity. So in the next video, I'll be covering one or two questions related to this modulo inverse, and we will see how it works. Stay tuned until that. Stay tuned. Stay safe. Bye-bye.